audience for today are mostly aeronautical engineers. Maybe some of the crew may also join in, and people from academic background, as well as people who are currently working in aviation sectors in different fields. So this is one of our effort to bring light to the aeronautical engineers and all our talent and knowledge that we can utilize in different aspects throughout the industry. So without much ado, I would like to invite you again, and I would like to pass the center stage to you. Up to you, Jose.
Okay, thank you very much. It's a pleasure to talk with all of you. Sorry about the time. Yeah, I know it's for you. It's better during the morning. Yeah, but since I'm in Brazil, it's like a little bit tricky. Yeah, to make this presentation to everyone. So for you, it's 6 p.m. For me, it's now 9:15 in the morning. Yeah, so that's why I asked for the change of the time, yeah, of your usual webinar time, yeah. So let's go for the presentation. I hope it's like enlightening somehow. I try to make it really, let's say, non-technical, because I know that Jivan made like a great presentation before with a lot of information about what the flight operations engineering are working on. So I'm just trying to bring here some view on that, like on different high terrain scenarios, how it affects performance. Really simple things, yeah, just to like review some concepts that for some people will be really basic. So sorry about that, but since the audience, I didn't know how it would be. But if it's too basic, or if you have any doubts, just shout. Doesn't need to wait for the end of the presentation. I can answer any questions that you have during it. Yeah. So just to introduce myself, as I said, like a different haircut, but it's still me. Yeah. I'm currently founder of Simpfly. It's a new company that we provide basically flight operations engineering services focused on the implementation and administration of electronic flight bags, yeah, the EFBs. And we are trying to do this to make life easier and simple especially for small operators and startups. Yeah, and I've been working in the aviation industry, mainly on flight operations engineering for the past 13, almost 14 years. Yeah, so that's why I was invited to talk a little bit about this kind of scenarios of high terrain, because it's where you are basically based on high terrain, yeah, and to see a little bit of how aircraft performance is considering this kind of situations, yeah. So to start the presentation, I just wanted to go through some just basic concepts and understand what are the risks involved, yeah, involved and enhanced when we are considering a high terrain scenario, yeah. So basically, the first thing it's really straightforward, yeah. So it's obstacles, yeah. So this is basically a safety hazard when we consider that it's possibility of aircraft collision, yeah, with mountains. So I'm bringing here just like an illustration of like what is a safety risk assessment matrix. This is based on the definition of the ICAO doc 9859. If you are interested in checking it a little bit in more details, I'm just bringing here really simple to see. It's basically like based on the probability of something to happen and the severity of the event. Yeah. So when we talk about severity, the worst thing that it can be, it's like catastrophic until going for hazardous, major, minor, or negligible event. Yeah. And for the probability, from something that is extremely improbable to something that can be frequent. Yeah. So you are going to try to avoid exactly the red part, that is what we call like intolerable events, let's say risks, yeah, that you cannot be in this region. The tolerable part is what we consider like it's tolerable if there are some mitigations in place, and that the risk that is still involved is acceptable by the management, by the company, and even by the authority. Yeah? And acceptable is something that it's fine the way it is. Yeah. So I'm just going to highlight here is just like when we talk about aircraft collision, yeah, or we're talking about high terrain itself. Basically, we are here. Yeah, we are here in catastrophic. In some cases, it can be like hazardous. Yeah, because catastrophic it's when you basically you lose the equipment or you lose lives. Yeah, and hazardous basically it's like you really reduce the margins and you can damage somehow the equipment. Yeah, and you might have some injuries. Yeah, so in case of high terrain, and let's say in case of like a depressurization that you need to to go for emergency descent, or in the case of a takeoff that you're going straight to the mountains. This is something that I would consider always like a, when I'm doing this risk assessment, I will always consider it's like a catastrophic event if something happens. And what we are going to try to do is exactly like how we go for something that is in the red zone to go for actually the yellow zone. So this is what is interesting in this matrix. It's like, even if it's something that you work hard to make it like extremely improbable to happen, it's still like in the yellow zone. So it's just like you always considering that you still have some risk. Yeah. And what you're doing here when we are doing this kind of studies and preparing material for the pilots, it's basically to be here. Yeah. But we are still in the yellow zone. This is important to remember. Yeah. When we do this kind of studies, as Jivan presented, like making sure that all takeoff performance analysis has obstacles considered, some turn analysis is made. It's always to reduce the probability of something happen, but you're still like in a risk zone, but it's like a tolerable and controlled one. It's a controlled risk, yeah. So in the end, what we do here is always like producing material to the crew to be comfortable, training, yeah, and always communication and everyone understanding what is happening. Yeah. So I'm just bringing here like as an examples, yeah, like of high terrain, yeah. And I made like my own list here, so it's it's not something from anywhere else. I just consider like here for me what I consider for aviation. There were top 5 major mountain belts that it's where you're going to find most of this kind of scenarios, this kind of studies. So to start with, basically it's where you are. Yeah. So I'm sorry, I don't want to, hope no one gets mad with me, but I consider here like that's why I said like a belt. So I included here the Himalayas together with the Karakoram range. It's like physically they are different, but it like the location, and since they are really together, I consider this like a single thing. Yeah, I think you're familiar with them more than me. The second part, it's like I consider here like the Zagros Mountains is this region in Iran. I'm considering this, it's not like a really, let's say, the most high terrain that we have in the world, but the thing is like we have a lot of flights here, yeah? So people that are flying from, let's say, Middle East to Europe, they always fly over here. And even like, I think for, if you're, even from South Asia, yeah, if you're going to Europe, sometimes you go through here. And I consider here the Alps also like basically overflying happens a lot, yeah, because of Europe, although it's not like a really long route over this as you have in the China, in the Himalayas region, yeah. But you have a lot of important airports here, yeah, that have like questions with high terrain. And then we have the Rocky Mountains in North America. It's also like if you go, the Rocky Mountains more like in this region, but it also has like I consider it's everything the same, but it's here it's like what they call like I think Alaska mountains or something, but it's almost like the same structure, yeah, formed by basically by the same how can I say the volcanic events, yeah. And the last one that I consider here is the Andes in South America. That is actually the longest mountain range that we have in the world. It's not like the highest, but it's the longest one. And these are my 5 ones, but I'm bringing here just like as curiosity 2 bonus here. It's just like there is like a really big range of mountains in the Antarctic mountains. So you have some flights there, yeah, but it's not something, let's say, commercial flights. So I'm focused more on the commercial part. And there's also like the Ethiopian highlands. I consider this as a bonus because it's like Ethiopian is the major airline in the African continent, but it's limited in this region, and it's not like there are a lot of flights compared to all these other regions that I mentioned, yeah. More than that, you're going to have other places with, you have the Ural Mountains, you have like the Atlas Mountains in the north of Africa. So there are different places that you're going to have this kind of high terrain studies, but I just wanted to highlight these ones as a way to understand that it's not only a problem in Nepal, it's something that it's considered in different parts of the world, you know? So here, just like some kind of examples. I was going to make like it as a quiz to see if you could guess what it is, but I couldn't prepare like a proper way to do this quiz in the presentation here, but just giving like a few seconds for you to look at this. And actually, I think the right one is the one that maybe you can be more familiar. This is in Bhutan. It's Paro Airport, and this picture is actually from it's from the forgot the aircraft. I think it's the 737-800. Yeah, 737-700. This is from 2003. It was like some test flights they did there to demonstrate the capabilities of the aircraft, yeah, on high terrain, yeah. So Paris, like the surroundings is as high as 18,000 feet, yeah. So it's one of the world's most challenging airports, and few pilots are certified to land there, yeah. So it's this kind of airports is used by manufacturers to exactly to demonstrate the capabilities of the aircraft in high terrain, as well as the left one in the bottom corner, yeah, at the corner. This one is actually Lima in in Peru. And it's also used for a lot of tests there, more than actually Paro. Oh, sorry, it's not it's Lima, but it's the airport name is El Alto, yeah, and it's the highest international airport in the world, with like an altitude of 13,325 feet. So the more modern aircraft that we have so far, yeah, it's like the A350, the new version, yeah, the XWB, and the 787. They were certified for high terrain in this airport, yeah. And the top one is just to exemplify that you have this kind of high terrain in different parts. This is in Tehran. This is in Iran. Yeah, this is the domestic airport in Iran. It's not like it's not compared to these other two that I said, but it's something that needs to be considered there as well. Great. So once we know about this concept of obstacle, that it's really easy to see, then the second thing that I consider is like a risk is exactly like the high altitude itself. Yeah, it's not only the obstacle, but the high altitude, it makes you having a lower performance, yeah, for the aircraft. Yeah. So basically, I'm bringing here this is basic, okay? I'm not going to make like really technical, but when we consider like flight mechanics, basically what you have is this, yeah? So what makes the aircraft flight, yeah? So you have like basically four resultant forces, yeah? There is the thrust, the drag, the lift, and the weight, yeah? So to make the aircraft fly, you will need to have these forces somehow to have some more thrust than drag, yeah, to be able to fly. And the more that you have the difference on that, the more you have the lift, so you can fly, yeah. So you also have, like, I didn't sometimes people don't consider it, but actually you have also the variation, yeah. Basically, if you have like if the aircraft is changing altitude, yeah, in the end you have this, let's say, acceleration, yeah, in the line of the thrust and the drag. So you need to compensate for that, and also you need to compensate for the variation on the flight path angle, yeah. So these are like forces. So you actually, this is like a centripetal force, yeah. So it's basically, if you go for the second Newton's law, yeah, it's just like force equals mass and acceleration, yeah. So this one is basically this is the centripetal one, and this is the straight acceleration, yeah. So why I'm bringing this is just like to remember you that what the high terrain will affect it, yeah. So we all know that the elevation, it will affect both how much lift the wing can produce, and also how much thrust the engine can produce, yeah. So I'm going to bring like just a small video that I took from Flight Insight in YouTube. I'm trying to reproduce here, but I don't know if you're going to hear it. So let me see if it goes with audio or not. Let me know.
Pressure and density altitude play a big role in performance calculations on the test, and it's a consistent weak area.
Yeah, we can hear that clearly.
You can hear? Okay, so I'm just going to play. It's just like 3 minutes, 3.5. It's just like some really small concepts. I'm bringing this basically for like people that are not familiar with the basics. Yeah. So just to understand what is the effect that it's going to have in the performance with the altitude. Yeah.
So let's have a look at it here. In low pressure air, air molecules are spread out. There isn't as much air in a given space when the pressure is low. When the air pressure is high, those air molecules become more tightly packed and the air is denser. Aircraft performance depends on this density. The propeller is more effective when it's pushing more air molecules to produce thrust. The wing generates more lift when it's pushing more air molecules downwards, and the engine produces more power when it has more air molecules going into the cylinders to combust. The pressure of the air changes as we move up in the atmosphere. At lower altitudes, aircraft experience higher pressure due to the compacting force of all of the air molecules above it pressing down. At higher altitudes, there isn't as much of this air pressing down, and so the molecules are more spread out and the pressure is lower. Aircraft performance is poorer at higher altitudes. Heating an air mass causes its molecules to move faster and spread out. Higher temperatures create lower pressure air. Aircraft performance is poorer in hotter temperatures. Changes in weather conditions give rise to high and low pressure air systems on different days. Aircraft performance is poorer on days with low pressure. Water vapor present in the atmosphere on humid days reduces the density of air. Bigger water molecules push or crowd out air molecules out of a space of air. Aircraft performance is poorer on days with high humidity. If we look at all these factors that are at play on a particular flight and say something about how well the aircraft will perform, we're going to be using pressure and density altitude to say it. In other words, after looking at things like altitude, pressure, and temperature, we can say that the aircraft will perform the way it would at a certain altitude under standard conditions or under conditions where temperature and pressure are held to a constant. First of all, if the aircraft climbs, it'll perform worse. So the true altitude of the aircraft is a determining factor of performance. Here it is at 8,000 feet. Now, if the pressure falls or is lower than the standard 29.92 inches of mercury at sea level, the aircraft will perform not as though it were at 8,000 feet, but as if it were at, say, 11,000 feet under that standard model. In Fantasyland, where pressure and temperature are held constant, this aircraft would behave as if it were at 11,000 feet. This is its pressure altitude. Similarly, if the temperature rises and air molecules spread out, the aircraft will behave as if it is even higher. So raising the temps causes the aircraft to perform not as if it were at its pressure altitude of 11,000 feet, but at what's called its density altitude of 12,000 feet. The definitions are: pressure altitude is true altitude corrected for non-standard pressure, or the altitude indicated when the altimeter is set to 29.92. Density altitude is pressure altitude corrected for non-standard temperature. So it's a multi-step process to get to density altitude. So just to review, an increase in altitude causes an increase in density altitude, a decrease in pressure causes an increase in density altitude, and an increase in temperature causes an increase in density altitude.
Okay, so yeah, it's just like a basic concept on to understand why we need to consider like a lower performance when we have like a high altitude scenario. Yeah.
Pressure and density altitude.
And the last part that I'm considering here for the concepts are like other contributory factors that actually they're going to reduce the margins and decrease the situational awareness of the pilot. Yeah, when we are talking about high terrain scenarios. So I'm bringing here some of these contributory factors, thinking about like the most of them that contribute for one kind of event that it's called like a controlled flight into terrain. Yeah, so it's when the pilot simply the crew simply flies the the aircraft is totally under control, but the pilot inadvertently fly into terrain or into water or into an obstacle. Yeah, so it's just like there's no problem basically with the aircraft itself. Yeah. So in this case, I'm separated this in three categories. Let's say so. Weather, it's one of the factors. Yeah. So if it's raining, if there's a turbulence, if there is icing, basically poor visibility, these are contributory factors to reduce the margins. Yeah. Sometimes for the performance. Yeah. In case of icing and rain, and for the pilot awareness. Yeah, because of visibility. So you're flying basically instruments. Yeah. So in the approach, you have some cases of like when it's the chart is unclear. Yeah, so the pilot has difficulties to understand what is the procedure, and it's common to have this kind of issues when it's like a new airport that they are flying to. They are not familiar with it, so basically you need to mitigate this with training. Yeah, and some, let's say, airport brief about these issues. Yeah, and there are some procedures that are too close to terrain. Yeah, depending on the region. Yeah, so if the crew is not familiar with that, this is going to actually reduce the margins. Yeah, for the flight. Yeah, and of course fatigue. Yeah, so there are anything related to the human part. Yeah, so fatigue, the pilot's workload, if it's all what I said before, like weather, unclear depiction of the approach, all these kind of things, they increase the pilot workload. It can make like more stress situation, and sometimes it can even lead to a disorientation. Yeah. So these are like contributory factors that it's even worse when you are considering like a high terrain. Yeah. And just like a reminder here, just like most of these events of controlled flight into terrain are due to loss of situational awareness. Yeah, it's not like something that happened with because of the it was a rainy day. Yeah, but it's because it was raining. There was some workload for the pilot. They lost the awareness of where they were. Yeah, and say they simply go straight to a mountain or just ignore some warnings in the cockpit and go to water and all these things. Yeah? So this is something that happens in these kind of situations. Yeah. So basically, these are the concepts that you need to understand when we are talking about the high terrain scenarios. Yeah? It just like it really reduces some margins, and it's really like in terms of performance, it reduces the aircraft performance, so the margins are lower, and it's really a major hazard, yeah, for aviation. Yeah. So here I'm just going to bring two case studies, yeah, about this in different situations, just to illustrate. I'm not going to be too technical here, but if you want more information on that, feel free to contact me or to interrupt me if you feel that it's missing something in the presentation. But the first case that I'm bringing here is like Enroute depressurization. Yeah, so the aircraft is flying, and for some reason it lost the cabin pressure. Yeah, and because of that, you need like to provide oxygen to everyone inside, and the oxygen provided is limited, so you need to go down in an emergency descent to an altitude that actually it's fine for everyone to breathe without any extra oxygen. Yeah. So this case here that I'm bringing happened in Peru, in the Andes. just, it's not this aircraft, of course. I just like to show you the picture of how it is there. And here's the case. So the flight that I'm talking here about was flight 1521 from Aviation Airlines. It's a scheduled and charter operator. Actually, it's not from Peru, but it's from Venezuela. And it happened on December of 2019, yeah, from a flight that was leaving from Lima to Tarapoto. It's another city in Peru. The aircraft was a 737-400 with 133 passengers and 8 crew inside. And what happened is like after they safely landed, some people actually ended up suffering a lack of oxygen, including a 6-month-old child. Okay, these pictures here are just to illustrate how was the aircraft after the incident. Basically, like I'm not going to go into details of the incident itself, yeah, because it's like our focus here is on the performance, yeah. But basically, the lack of oxygen that happened was because like people didn't know exactly how to use it. Some of the masks, they forced it simply they break the mask, and so they needed to change places, yeah. And yeah, in this first picture, and the second picture is just to show what actually happened. The investigation showed that actually it was like these blankets, these isolation blankets inside one of the compartments of the aviation. They simply a maintenance work. They left these isolation blankets loose, and during the flight, they went through the outflow and obstructed it, and also the safety relief valves. So these are something that they control the pressurization, and because of this failure, that's what happened. Yeah, so it was like a maintenance issue. I think like it is in the report. I cannot remember right now, but actually it was like something that was not maintenance. Actually, they were looking for some, let's say, some investigation if there was some like inspection actually, yeah, for looking for drugs or anything like that. And after that inspection, they didn't put the blankets, the isolation blankets in place. Yeah. So that's what happened. That's what made the incident. Yeah. So here you can see better the route, and this is actually more than as everyone knows. This kind of events in aviation doesn't happen for a single thing. So you actually the loose blanket made like the problem with the pressurization, but we have another thing happening here is like the flight itself was to happen from here. Here's here is Lima, right? And they needed to fly to Tarapoto here. Yeah. So actually, the flight plan that was filed is through this route here that I'm showing. It's in the, let's say, in the shore, yeah, the Pacific Ocean here, and after that going inside, yeah. So you're just going to cross the Andes in this region here, yeah. But what happened was ATC offered for the crew to fly the direct route, yeah. So from here to here, the blue line here, yeah. But the thing is, you can see here that actually going this direct route, you go through checking the grid model here only. You can see that you're going to go through a much higher terrain than the planned flight. Yeah. And you will see that actually in this region here, there are no suitable alternate close by. There are only like two really small airports in the middle of the mountains that are not suitable for like a 737. And this this chart here that I'm showing is actually what you find in the Aviation, let's say, ops manual. Yeah, so this is like a depressurization chart, yeah, escape route chart. So it shows that actually they were prepared for any kind of depressurization. Yeah, they did the analysis, but they did the analysis considering this route here. Yeah, so if something happens during this flight, during this route, it shows what the crew should do. Yeah, to return, to continue or not. Yeah, but there was no provision for this blue route here. Yeah, so I'm just changing here for like a chart that I took from the Jepsen application for EFB. I hope they don't sue me to show this here. Yeah, but it's just like because it's easier to understand what happened. So you can see that actually they took this route here, and you can see the terrain. Yeah, so it goes long way through this high terrain here, and here's where they actually had start the emergency descent near this fixed manner, and they deviated. Instead of going direct, they deviated to NPAP, and then they went all the way to the destination. That was actually the best option, yeah, for to continue the flight. Yeah. So I took like to analyze this incident in terms of performance. I was analyzing like, okay, so they were not supposed to fly there, yeah, and they have like depressurization. I see there was a question. Let me.
Yeah. Yeah, I think we can answer the questions at the end of the presentation. That would be if you are okay with that.
Okay, yeah, for me it's fine. Yeah, so I'll leave it for the end. But as I said, I don't mind if to be interrupted and answer in the middle. Yeah.
Yeah, it's up to you actually. So if you think it's better to.
Yeah, I will consider if something that I didn't answer during the presentation. Yeah, and if you like, just let me know. So actually, like, here you're going to see that actually I just took this as like to illustrate you, so I could understand. Yeah, when I'm trying to understand a route, the first thing that I do is like to check the terrain. Yeah, so I just took like here from Google Maps. It's not doesn't have the margins that are necessary to when you're considering like a flight path. Yeah, I'm just to see like how is the profile. So you can actually see that, let's say near here, like from Ural, yeah, that is somehow here, until let's say here, yeah, where they started the emergency descent. All this terrain, it's above 10,000 feet. Yeah. So if you remember, yeah, this like 10,000 feet is the altitude that actually it's fine for a depressurized aircraft. Yeah, without pressurization, it will be fine. But anything above this, you will need to provide extra oxygen to the passengers and to the crew. Yeah. So actually, I'm just checking here to see like, okay, so this is the region. Probably this is the region that it's critical, and it's right. It's really like a long way, yeah, to consider for the type of the aircraft that I'm talking about here, as you will see in the following slides, yeah. So the first thing that when I saw this incident, I was looking like, okay, so let's face it, like, what happens if this depressurization happened before, yeah, this point, what it happened, yeah, because if it was not considered in the escape routes from the company, probably because they realized it was not possible to fly that way, yeah. So as you see, like, the incident happens to a lot of factors, yeah. And in this case, I'm just trying to look on the aircraft performance side, yeah. So when I'm going to do this kind of analysis, and even if it's like, doesn't need to be like an incident, yeah, but if it's like let's say someone wants to fly to a new route, yeah, and I want to know if it's possible or not. The first thing that I need to do is to check, like, is the aircraft able to proceed or return through the same flight path if something happens, yeah. So I'm flying there. Do I need, if something happens like a depressurization, can I continue the flight, or am I still able to return in the same flight path? Yeah. If not, then I need to check, like, is there any feasible alternates within the flight path? Yeah. So just like I continue, but I just descend and land in a alternate. Yeah. If none of this is possible, then it's my last resource is actually I need to determine some point of no returns for to make a diversion, yeah, to some feasible alternates. So this is like just a quick review, yeah. So I'm just, as you see, like, Ivan just presented this already, yeah, in the last webinar. So what I'm just bringing here is just like for this 737-400, this is what we have for the aircraft. So on the left, you see the oxygen system profile, yeah? So basically what it means is like, this is where you guarantee that you have enough oxygen for everyone if you are flying below this line, yeah? So let's say, for example, you have a depressurization somewhere here, like flight level 330. Let's say after like around 2 minutes, you need to start to descend until you reach, let's say, flight level 170 after 5 minutes from the beginning, and then you can continue for around 6 minutes, yeah. And after that, you need to descend again to 10,000 feet, yeah. This is to guarantee that you're not going to have a lack of oxygen, yeah. And this is because this aircraft of the incident, it has like a 12 minutes oxygen system. So that's why you have like this 12 here. It's just like, it guarantees that it has like enough oxygen for 12 minutes until you reach this 10,000 feet, yeah. At the same time, I'm just bringing here, like, this is from the AeSN or the QRH, both ops manuals provided by the manufacturer on how the crew would do this emergency descent, yeah. When you do an emergency descent, it's something that you really need to go down as soon as possible, yeah. So in this case, I'm just bringing it here just to see that actually what is an emergency descent is basically like you're going to make sure to try to do as fast as possible. So MMO and VMO, it's like maximum Mach and maximum speed, yeah, to go down and to descend to 10,000 feet. That is what we want, or the minimum safe altitude possible, yeah, whichever is higher, yeah. So if you cannot go to 10,000 feet because of obstacles, yeah, because of terrain, so you go to a higher altitude until you can descend more, yeah. And of course, there's always the judgment of the pilot. If like there's any structural integrity problems, then you need to maybe limit the airspeed, yeah, to avoid any structural problem, yeah. So here is the analysis that I did. So as I said, I'm not being too technical here. I'm bringing how I did all the calculation, because actually I saw that Jivan have made some of these the points that you need to consider, yeah. But basically, what we do here is like the flight, the incident. They were flying. The cruise level was 330, so that's what I consider in the analysis. I consider like the weight, the wind, the worst case scenario possible, yeah. And I took all the terrain that I showed to you in the Google Earth, but I considered some margins here. So you had like indications of the segment that I said was critical, yeah. So it was I was considering it was between Euro and Nanner. So you can see that actually I was kind of right, yeah. But it's you still have like high terrain even before Euro here. So when I do this analysis, yeah, what we do is like, okay, so if the failure is in any of these points, yeah, can I continue? Can I go back? Can I continue? And what I found out was that, yeah, so actually until this point here, I can actually still return, yeah. So I can make like a return and come back to the same flight path, yeah, and still avoid the obstacles, considering my emergency descent profile, yeah. And if I'm in this point here, I'm calling PNR2, I can actually continue the flight, yeah, with avoiding all the obstacles with the necessary margins. However, if I'm between these 2 points, I cannot do any of this. I cannot return without hitting the obstacles, or continue the flight before hitting the obstacles, yeah. To make sure, of course, that this is not like a, let's say, an aircraft performance thing. It's just like because you're limited by the oxygen, yeah. So the thing is like this flight actually, the depressurization happened here, yeah. So actually, fortunately, it happened like almost in the end of the Andes, yeah. So since it happened after this PNR2, actually they would be able to actually to proceed the flight, yeah. So if you consider like here, this was like you can actually calculate the distance here, yeah, from this point here to this, and considering the speed, yeah, it's like it's like around 30 nautical miles, yeah, from the point of the incident and the PNR2 that I calculated. And considering that they were flying on Mach 74, at this altitude, it's around like 262 knots. Yeah. So actually, this was an incident. Yeah. But if it happened like 5 minutes before, maybe it was an accident. Okay. So this is the message that I wanted to bring for this incident in the Andes. That sometimes it just go like people just try to focus on like, it was a problem with in communication. It was not the ATC to provide this route. The crew shouldn't accept it as well. There was an issue with the inspection, so there's a problem in maintenance. All these are correct, yeah. But as a flight operations engineer, as an aircraft performance engineer, we should always take a look on this and see like how to give like one more protection, yeah, one more protection level to anything. So, of course, they had it, yes, because they didn't have this procedure in the escape route manual, because actually they consider it cannot be flown this route, yeah. So actually I didn't put it in the presentation here, but actually I did some studies if it was possible to make a escape route there. And through my analysis, it was a simplified one, yeah. But I found that it was possible to do some escape routes, but it was really like really tight margins, yeah. So probably if I was going to publish something like that, I would need to consider more restrictions, more scenarios, yeah, to publish it is as something to give to the crew, yeah. Anyway, this was the first case, so the first study case that I wanted to bring to you, and since it's already like a little bit, we're already here almost 1 hour, yeah, but we started a little bit late, so let me go to the second case. So I'm bringing now a different situation. It's like an engine out during climb, so it's like a failure after V1. So it's a different scenario that actually the aircraft performance engineer needs to consider, not only the regulatory takeoff, yeah. And this is basically, I'm bringing exactly a case that it happened like in Denver, yeah, in Colorado, close to the Rocky Mountains, yeah. So this is the view that you can see from the airport. So this is like like a front range in the Rocky Mountains that is close to the airport. It's not that close, yeah. It's like more than 25 nautical miles from the airport, but the airport itself, it's like in a flat land, but it's in a high land, so it's more than 5,000 feet, the airport. And this is probably you heard about this incident because it was this year and it's really recent. And actually, it was like an engine fire. It was the flight from United Airlines, the flight 328 on February. It was leaving from Denver to Honolulu in Hawaii, and it was a 777, yeah, with these Pratt & Whitney engines. There were like 231 packs on board, plus 10 crew, and fortunately no casualties, yeah. This incident is still under investigation, but there's like already some FAA already issued like a airworthiness directive about these engines. Most of these aircraft with this kind of engines were grounded, yeah, including in the US. And the American NTSB, that is the National Transportation Safety Board, is still investigating, but basically there's some issue with this engine, yeah. But they were not actually the 777. It's with this engine. It's no longer manufactured, yeah. So actually, most of the aircraft is with a different engine, yeah. And actually, as far as I could see until now, United didn't return all the 777s, 200 with these PW engines to service yet, yeah. So because of this investigation that is going on, our focus again, it's not on like what made this, what contributed to this event, what happened to the engine, but more like on the flight itself in terms of the high terrain. Yeah, what was the risk involved in this flight? Yeah, after the engine failure. Yeah, so I took here this from Flight Aware. So actually, we can see the flight path that was flown. You can see here the start of the Rock Mountains, the front range. Yeah, so Denver is here. Yeah, and you will see through this video like the flight path that they did, and also you can follow here. The yellow line here is the speed, and the green one, sorry, is the altitude. Yeah. So it's, unfortunately, the speed is miles per hour, but you can see how it goes. So it returned to Denver. Yeah. And it took off from runway 25, and it landed in runway 26 is another one. So actually they have like, I don't know, 1, 2, 3, 4, I think like 4 runways or 5. It's a big airport there. So just let me go again here and let me try to pause. So actually the event was somewhere here. Yeah. So actually you can see, yeah, it was climbing. And I think it was, yeah, so they started like continuous constant speed, and somewhere here, yeah, close to 10,000 feet, they were flying over this neighborhood here, and they noticed the engine failure, and they called for Mayday, and they returned to Denver. So they start making like this left turn, and they return even before flying over the mountains. Yeah. So the same thing as the other event that I brought. Like, okay, I was just analyzing this. I say, okay, but what if the engine failure happened like after this? Yeah. What if it happened here? Yeah. And also what about if the weight was different? Yeah. What about if the environment conditions were different? Yeah. So that's the work of the of the aircraft performance engineer. Yeah. Like, let's try to look on the worst case scenario. Yeah. Because fortunately nothing happened here. But what if the situation was different? Would we be the same? Would we need to do something about that? Yeah. To avoid this incident to become an accident. Yeah. So I just reproduced this procedure, the flight here in Google Earth again. So you can see, I could find out that actually they were flying this Zimmer 2 RNAV procedure. There is this blue one. So this was the planet flight path, and you can see that actually the failure happened somewhere here, and they make the left turn before Ralphie, yeah, and they return, yeah. So what I was going to analyze here was exactly like this. Okay, let me check. What if it happened in different place? Yeah. So I just took like here again. This is like a Jepsen chart. Again, hope they don't sue me. It's just because it's easy to see here. I'm just showing how I could find out that this was the route. So actually, this is runway 25. So I can see that it went all this way until here, and then it comes back. And here you can see actually the distance between each fix, and also some of the constraints of this procedure. Yeah. So I'm bringing here the full chart. Yeah. So you can see there are some. It's really small letters, but I'm going to bring the FAA chart now after this, just because this one you can actually see the terrain that I'm considering. So it's it can goes up to here. It's like almost 15,000 feet. Yeah. So this is like a critical region, even though it's kind of far from the airport. It's like this circle here. It's like the 25 nautical miles from the airport. So let me go to this FAA chart. So this one is like a public chart, yeah. Then you can actually see I highlighted here something from this route here. So you have like some minimum climb that you need to consider to fly it, and also some speed that you need to reach, and also this flight levels, yeah, this altitude. So actually, in this first fix here, you need to reach it at 10,000 feet or below, yeah. This one you need to reach at 12,000 or above, 14,000 or above, 16,000 or above, or 17,000 or above, yeah. So what I did was exactly like similar to the other example. So I just took like Google Earth to see how is the terrain profile. Yeah? So actually I could see that actually my critical part is exactly between Ralphie and Zimmer. Yeah. Because after that the terrain goes down. So actually if I can clear terrain until this point here, I would be fine. Yeah. And you actually can see that it's like 25 nautical miles from the airport and 45 nautical miles. So actually, by experience, I can tell that it wouldn't be a problem actually, yeah, because it's kind of far. But anyway, let's analyze it, yeah, because that's our job, yeah. It's not like just to guess things, but actually to check it, yeah. So here again, like, what are the kind of steps that how I think when I see these kind of things, yeah? So the first thing that I would check is like, okay, can I fly this procedure always, yeah? This is like a SID, yeah? So as an engineer, I need to check, especially on these kind of airports, and you have even worse ones, let's say, more complex ones in your region. So the first thing that you need to check is, okay, is the aircraft able to keep these SID gradients that are in the chart, yeah? You couldn't see, like, let me go back here. Okay, so these values here are the climb gradients. They are in feet per nautical miles, but you can put it like in percentage as well. So can I keep that gradient even in case of an engine failure? Yeah. So probably you can do it like with all engines, but what about if you lose an engine? What will be your gradient? Can you still keep flying this SID? If not, can you still clear all the obstacle if you follow that SID? Maybe you're not going to respect the published gradients required, but maybe doing an analysis on like let's say an obstacle clearance climb gradient, can you still proceed without any risk? Yeah. So with enough margins from the obstacles. And in the end, like, if not, as a last resort, is like, okay, so we'll need to do similar to the escape route. We need to actually to define like a decision point where if the engine failures happens before that point, you need to return, yeah, or make like to design an engine out procedure. Or if it happens after that point, you need to continue. Yeah, it's like this is the idea of the decision point. Yeah, it's just like the point that actually you can assure that if it happens after that, the crew can still continue the SID if needed. Yeah. So in this case here, as a worst case scenario, what I consider is like, okay, we're in Denver. Yeah, so taking a look on statistical data, you can actually check historical data, what it can happen there. So I consider here, for me, I consider like, okay, my worst case scenario would be like a rainy day during a hot summer, so 30 degrees Celsius, and worst case wind that would be like around 10 knots tailwind, and with maximum takeoff weight. Yeah, so I'm considering like, okay, maybe I can be like with a full packs, full cargo, maximum fuel, because like let's say during a non-pandemic high season and a long flight. Yeah. So in this situation, the first thing that you should do is okay, it's like for all engine operating. Yeah. Can you do this? So I took here like this is like from Boeing OPT. It's like a EFB software for the pilots. So actually pilots should check this before flying. Yeah. So they need to check based on the charts. Okay, will I respect the climb gradients that are published there? So actually you can see here that yes, it can, even in this worst case situation that I gave you. So it shows that actually the minimum gradient is 3.3 in the beginning, in this part here, but in the average, it's 5.5. And this one that I put here, like as the minimum required is the one from the chart that I highlighted in yellow. It's like 3.78%. So it goes up all the time, above this all the time. So there is no issue for the all engine. Yeah. But in the case, so all engine is okay, but what about the one engine? Yeah. So in this case, I did like a really simple study here, because I don't have data and access to the proper aircraft performance tools from Boeing for the 777. And so actually what I did here is like, as in the previous slide. So actually, okay, what about like this all engine climb gradient if I lose one engine? I could make like a really simplified calculation, and I can actually could see that actually you couldn't do this with the 3.78% in this worst case scenario that I did. But actually, if I consider only like the obstacle clearance, I will get like a gradient of at least like 2.03%. So I could actually clear that obstacles and continue. So I wouldn't need like to define like a decision point and do an engine out in this case. Yeah. So this one I couldn't do like more of a work here, but for sure like United has like a really experienced and big flight operations engineering department, and for sure they were really covered here. Yeah, so it's not something that they were missing. Yeah, it's just like they already knew the flight was possible. They already had, I don't know if they had any let's say indication for the crew if something happens, if they needed to do like a left turn and come back, or a right turn. Yeah, usually you just do like a left turn, is just because it's easier for the captain, yeah, to do it. Yeah, or left turn. And so it's not something that exactly in this example here that I took, yeah, it was not like something really critical, let's say. Yeah, but even if it was, I'm pretty sure that United was covered. Yeah. So as a, let's say, as a reminder here, as my final wording here, I just took this from Neil Armstrong. Is like that. Yeah, if you've got to expect things are going to go wrong, and we always need to prepare ourselves for handling the unexpected. And this actually is exactly what flight ops engineers need to do in all these kind of things. So everything that we do, most of the time, actually, people will not. Hopefully, they will not even use what we prepare. Yeah, but it needs to be in place so the pilots have the best information for decision making. Yeah. So that was my presentation. I hope it was enlightening somehow. It was really simple. Yeah, I didn't want to go too technical. I just wanted to bring some examples of real situations and so actually you can link with previous presentation from Jivan and to see that actually it's real situations. Yeah, it's not something that it's just like it will never happen. It can happen things. Yeah, and that's why we need to consider all this kind of analysis on the pressurization and engine failure. Yeah, you have many more examples. I just brought like 2 here. Yeah, based like on high terrain scenarios. That it's something that it's really familiar to you. And I'm leaving here just like my 2 contacts. If you have any questions that you don't want to do here or you think later on. In my LinkedIn, actually, these 2 examples, these 2 case studies that I brought, one of them, the first one, I wrote an article and I actually explained a little bit more in details what I did. And the second one, I'm going to publish this article, if not today, like in the coming days, because I couldn't finish exactly the part of the calculation. That's what I just presented in the end here. I didn't end in the article yet. So that's it. I'm open for any questions, anything that any comments, any critical things. I'm just here to waiting for anything.
Yeah, first of all, thank you, Jose, for such a wonderful presentation. It was very interesting, and especially the part where you showed us the global perspective of the terrain, and also how even 5 minutes was so critical. Things could have gone so much wrong with that 5 minutes. So overall, thank you very much for your wonderful presentation. So there are a few questions that has been raised, so I would like to read out that for you.
Sure.
Yeah, so first question is from Prabhav Rekmi. So he says, in high terrain airports, the glide path of approach is very high. What are the risks involved in such cases? So this has not been covered, but I think some.
Yeah, I didn't bring any example on approach. Yeah, so the thing is like in high terrains, this one are actually, if I go back to, let me see if I can I go back here to, probably it was slide 6, no. This one, yeah. So actually, in the approach, what you have is exactly like the workload is higher for the pilot, yeah. So one of the risks here is like usually most of the approaches. I'm not a pilot, so if any pilot is here and wants to correct me, feel free. But most of the glide paths usually it's like 3 degrees, yeah. So some airports, especially in high terrain or let's say because of noise, you might have like a steep approach, yeah, or you might have like a non-standard approach glide, yeah. So it's going to be like 3.3, yeah. So whenever it's different from the standard, it's already a risk because it's like something that it's not usual for the pilot. So this is one of the risks, yeah. The other risk is like, as I said, like depending on how steep it is, you might have to have a special certification of the aircraft to do it, yeah. And for sure some extra training for the pilots, yeah. This is for the approach, yeah. But at the same time, if it's like let's say you're landing and you need to dismiss the landing, so to make like a missed approach, then you have like all the risk of that you have for the takeoff as well. So you're going to even though like for regulation for landing, you don't need to, you just need to make like analysis on the gradients. You don't need to do an analysis on the obstacle clearance as you do in takeoff. But this is something that actually as a flight operations engineer you need to consider, like, okay, if I do like a missed approach, do I need to can I follow the procedures on the chart, or does it clear all the obstacles? Yes, this kind of analysis you need to do. I don't know if this answer your question, but these are the kind of risks that I would usually associate with the approach in high terrain. And of course, all the other things, like all these other factors that I put there, like anything that it's happening, and it happens in exactly like everything that I told, like the performance is lower, sometimes depending on the high terrain, sometimes it's not always, but it comes with other things. The high terrain can come with like a different, like strong winds, or like so depending on the region, you're going to have, like, it's common to have like a poor visibility in the region because of that. So these kind of things are common.
Thank you, Jose. So just in addition to this, Jivan has asked one question. I think it's more for the audience. So for engine out condition, what would be the obstacle clearance criteria during approach and landing?
For engine out condition, what will be the obstacle clearance criteria during approach and landing? Okay. Yeah, so that's what I was telling, is like for regulations, for when you do like a approach and landing, there are no criteria for that, in the terms of regulation. The only thing that you have is exactly like for landing, you need to, the calculation considers two situations on the approach. That is like the approach climb and forgot the name of the second one. It's landing climb, I think. Two situations that is basically like you need to make sure that you respect a minimum gradient in these situations. So one of them is basically, well, that goes for the engine out condition, is like you're landing and you with only one engine before you land, you start climbing. So your configuration, it will be like a approach flaps, landing gear up, but then you need to consider like the minimum gradients that depends on the type of aircraft. I don't have the numbers here to present to you, but if I'm not really mistaken, it's like maybe 1.2% average, like something like that. If someone remembers that, it's just because I didn't bring anything on this part. But it's like it doesn't consider any obstacle in the landing analysis, But as we do, like as I showed for the engine out procedure, the SID, engine out SID, you should also consider like doing the same thing for the approach, So for the, let's say, the missed approach, you should do the same kind of analysis. It's not like a regulation, because for regulation you basically have like for takeoff and landing, the basic regulation, but for it's also covered by our job to do exactly this analysis on if the failure happens after V1. Yeah, this is the case that I brought. And for the approach, the same thing. Yeah, just like if you're in the high terrain, to do the same kind of analysis. And but like basically, there is no regulatory for that. Just like basic things like on considering like the same margins. Let's say this 35 feet from the with like from the obstacle, yeah, to clear it, yeah.
Oh, thank you, Jose. Actually, I was wondering some situations like, okay, we got an engine failure at B1, and we try to, I mean, we have an USID to land at the same airport. So, but and again, if we cannot land at a single attempt due to engine failure condition, which may be the probable condition, and so there we need to take a mixed approach, and so do we need to also consider the mixed approach during the USID design to land at the same airport? How is, I mean, how do you see this scenario? Because I've been wondering
Okay.
this kind of scenarios.
Yeah, usually when I consider like a engine out SID procedure, the design, I always consider like at least like to bring the pilot to a safe condition, exactly like I would do like in a failure at V1 or after V1. I would do like, okay, can I bring the pilot to a holding position? Yeah, at least like to for a decision point. So actually, because for the pilots, basically like there is like it's like a critical situation. Yeah, the first thing that they need to do is like to have control of the situation and to be like once it's controlled, to communicate and try to land as soon as possible. Yeah, so this is what I would consider, because in the end, like you will have situations, for example, that they will need to land directly, or they can still wait. Yeah, it depends. It will be like on their criteria. Yeah, and probably in this situation you're going to be like you're going to have like a overweight landing. Yeah,
Yeah.
so you can actually analyze this kind of things as well. Yeah, as a performance engineer, to check like, okay, how much overweight it will be, what will be
Okay.
the margins if
Thank
it's
you very
not.
much.
Yeah, just
Sorry.
no problem.
Sorry, I'm breaking up.
Did I answer your question?
Yeah. Thank you, Jose. Actually, I was wondering. I had this question in mind that how do we deal with this scenarios like just I explained. When you design the engine out seat and to land at the same airport due to the difficult terrain, and we cannot land with one engine, and we again have to do the mixed approach and again have to try to land. So I always had these
Yeah.
questions in my
But
mind.
like the regulated calculation for takeoff and for landing, they consider this one engine gradient. Yeah, minimum gradient.
Yeah.
But the thing is, like, usually the charts that are provided for this approach, they have like they were designed considering like some obstacle clearance. Yeah, but even if they do, it's always good as a performance engineer to check. Yeah, where it's going, because in the end, like usually this approach, it's considered for like all engine. Yeah, it's just like a misapproach because of other things, not because of engine failure. Yeah, it's just like because of
Yeah.
visibility or like a gust or wind. Yeah, some other situations. Yeah, unstable approach. Yeah, so anyway, it's
Yeah.
good also, like especially on really critical airports. Yeah, it can come to mind to check. Yeah. even if sometimes even the pilots will bring this to you, like they may be worried about something, and then you can analyze. But for sure, it's kind of covered. But as I said, like maybe this part of it's always good to check, because it's like usually fought only on the all engine situation.
Yeah.
Thank you very much, Jose. Thank you for the answers.
No problem.
Yeah. Yeah, thank you, Jose, for that clear answer. So I think we have one more question that is from Sajin Sokant. So he says, hi, just a query. Noticed in the last slide that the emergency descent profile for continuing and turning back was identical in terms of distance covered during descent. In real time, shouldn't we give some margin for return, as aircraft may cover some time and distance during turn back? Thank you. So that was, I think,
Can you just give me 1 second?
yeah, definitely.
Someone is calling here. Just a second.
Okay, sure.